Hello everyone, I am Karthik, Assistant Professor of Mathematics, SNS College of Engineering. In this lecture video, I will explain about complex integration. Okay, Introduction to complex integration. To understand complex integration, let's first define what is complex function is. A complex function f of z is a function of a complex variable z, where z can be expressed as z equal to x plus iy, with x and y being real numbers and I being the imaginary unit defined as I square equal to minus 1. Concept of residues. Definition of residue function. The residue of the function f of z at an isolated singular point z0 is denoted by residue of f comma z0 if f of z can be expressed as f of z equal to summation an z minus z0 whole power n near z0. Then the residue is given by residue of f of z0 equal to a minus 1. The coefficient of z minus z0 whole inverse in the Lorentz series expansion of f of z about z0. The key points are isolated singular points, poles, removable singularities, evaluation of integrals, etc. Cauchy's residue theorem. Statement is, let f of z be a function that is analytic inside and on a simple closed contour C, except for a finite number of isolated singularities z1, z2, etc. zn. Then for any closed contour C that encloses the singularities, the contour integral of f of z around C is given by closed integral f of z dz equal to 2 pi I summation of k equal to 1 to n residue of f of z comma k. Next one, singularities and poles. Singularities. A singularity of a complex function f of z is a point in the complex plane where the function fails to be analytic. In other words, it is a point where the function behaves in a non-smooth or irregular manner. Removable singularity. At a removable singularity, f of z is undefined at the point, but it can be filled in with a single value to make the function analytic at that point. Residues at simple poles. First we have to know what is pole. A pole is a specific type of singularity characterized by its behavior near the singular point. Residue at a simple pole is, consider a complex function f of z with a simple pole at z equal to z0. Then the Lorentz series expansion of f of z about z0 takes the form f of z equal to a minus 1 divided by z minus z0 plus a0 plus a1 into z minus z0 plus a2 into z minus z0 whole square, etc. Next, calculation of residue. First one is Lorentz series expansion. Second one is limit calculation. Residues at higher order poles. Consider a complex function f of z with a pole of order m at z equal to z0. Then the Lorentz series expansion of f of z about z0 takes the form f of z equal to a minus m divided by z minus z0 whole power m plus a minus m minus 1 divided by z minus z0 power m minus 1 plus etc. a minus 1 divided by z minus z0 plus a0 etc. where a minus m is the coefficient of z minus z0 whole power minus m and represents the residue at the pole z0. Applications of Cauchy's residue theorem. First, evaluation of integrals. One of the primary applications of Cauchy residue theorem is the evaluation of complex integral. It allows for the computation of integrals that are difficult or impossible to evaluate by standard methods. Next one, inverse Laplace transform. In engineering and applied mathematics, the residue theorem is employed to find the inverse Laplace transform of a given function. Real integrals. Cauchy residue theorem can be applied to evaluate real integrals involving trigonometric, exponential or rational functions, etc. Solving differential equation. The residue theorem is employed in solving differential equations with singularities in a complex plane. Overall, Cauchy theorem provides a powerful and versatile method for evaluating integrals, solving differential equations, and analyzing complex functions. Thank you.